Taklamakan. From a moving sea of sand to a green economic corridor, in winter, temperatures here can fall close to -20 degrees Celsius. Yet only a few months later, summer heat can push the air temperature toward 50 degrees. Within a single year, this land must endure both bitter cold and extreme heat. Rainfall is scarce. The air is exceptionally dry, and any moisture that reaches the surface disappears quickly. Meanwhile, the wind rarely stops blowing. This is the Taklamakan Desert, the largest desert in China and one of the world's largest shifting sand deserts. Seen from above, it resembles an enormous ocean from which all the water has vanished. In place of waves are countless dunes stretching toward the horizon, constantly changing shape under the force of the wind. Taklamakan is not a lifeless landscape that remains still. It is always moving. Whenever strong winds rise, millions of grains of sand are lifted from the surface. Entire dunes slowly advance toward roads, farmland, oases, and settlements. For centuries, this hostile landscape has been known by a frightening name: the Sea of Death. Yet today, a highway runs directly through this moving sea of sand. Its dark surface cuts across the golden desert like a line drawn toward the horizon. Trucks, buses, and private vehicles travel along it every day. On both sides of the road stand long rows of drought-resistant trees, forming green corridors that extend for hundreds of kilometers. Looking at this scene now, it is difficult to imagine that in the past, sections of this road could almost disappear beneath the sand after a single major storm. Sand would spill across the highway and force vehicles to stop. Excavators had to be sent in, while workers cleared the road in fierce winds and poor visibility. But removing the sand only solved the immediate problem. Once one section had been cleared, another wave of sand could arrive and cover it again. The disruption affected far more than traffic. Agricultural products could not reach markets on time. Machinery, construction materials, and daily supplies could not easily enter remote communities. Cities on opposite sides of the desert remained separated by an enormous and dangerous barrier. Sand also buried irrigation channels, reduced the amount of usable farmland, and advanced toward fragile oases. Taklamakan did not destroy everything in a single day. It moved forward slowly, sometimes meter by meter, but it never truly stopped. Without a way to stabilize the sand, every road, settlement, and field built near the desert remained at risk of being reclaimed by it. Look closely at the road now appearing beneath the drifting sand. What would you do first? Build a massive wall, plant trees immediately, or find a way to stop the sand itself from moving? Leave your answer in the comments before we reveal how this enormous project actually began. The long-term response took shape in 1978 when China launched the 3 North Shelterbelt program. It was designed to reduce desertification across large areas of northern, northeastern, and northwestern China. Taklamakan became one of the most difficult regions involved in that effort. The objective was never to turn the entire desert into a forest. Taklamakan is too large, too dry, and too active for such an idea to be realistic. Instead, the strategy focused on protecting the most important areas: the edges of the desert, oases, farmland, settlements, highways, railways, and transport corridors. Rather than attacking the center of the desert, engineers and workers built a layered defense around the places that needed protection. The outer layer was designed to stop the sand from moving. Behind it came grasses and low shrubs. Farther inside were drought-resistant woody plants and taller shelterbelts. Behind those living barriers were roads, villages, farms, and economic zones. The most surprising part is that this huge transformation did not begin with towering machines or advanced technology. It began with bundles of straw. Workers pressed straw into the surface of the desert and arranged it into square grids. From the air, millions of these straw squares resemble a giant chessboard spread across the sand. The method looks simple, but it performs an essential task. As wind passes over the grid, the exposed straw reduces airspeed close to the ground. Once the wind slows down, sand is less likely to be lifted and carried forward. Instead, it begins to settle inside each square. Every straw square acts like a small trap for moving sand. Thousands of squares create a more stable surface. Millions of them can form a protective zone extending for dozens of kilometers. The straw also helps the surface retain a small amount of moisture from fog, light rainfall, or irrigation. As it slowly breaks down, it adds a modest amount of organic matter to sand that contains almost no nutrients. Most importantly, the grid creates a brief period of stability, long enough for grass to germinate, and for shrubs to begin forming roots. This is worth remembering. A green barrier, more than 3,000 kilometers long, began with small bundles of straw pushed into the desert by hand. If you enjoy seeing how simple ideas can lead to massive transformations, subscribe to the channel now, as the aerial view reveals the enormous straw grid. The next stage is where a seemingly lifeless surface begins to behave more like living soil. Once the sand became more stable, grasses and drought-resistant shrubs were introduced. In many areas, workers planted young shrubs or inserted sections of hardy stems directly into the stabilized surface. The first plants did not need to be beautiful, and they did not need to produce fruit. Their first responsibility was survival. These species had to tolerate poor soil, high salinity, extreme temperature changes, and very limited water. Their roots spread outward or grew deep beneath the surface, helping bind sand particles together. Their stems and branches slowed the wind further, while their leaves captured airborne dust. When leaves and small branches fell, they created a thin organic layer on the surface. The changes were gradual but visible. Small green patches appeared between the yellow straw squares. Those patches expanded into strips of grass. Shrubs grew taller. The surface retained moisture for longer periods, and temperatures close to the ground became slightly less severe. This was the real beginning of soil restoration. The sand was no longer simply being held in place. It was slowly becoming an environment capable of supporting more life. But stable ground alone could not sustain vegetation. Taklamakan receives very little rainfall, while intense sunlight and dry winds cause water to disappear rapidly. In key areas, wells had to be drilled into deeper underground water layers. High-pressure pumping systems brought water to the surface. From there, pipelines carried it along the green corridors and toward the newly planted vegetation. The water could not simply be released across the sand. Traditional flood irrigation would waste too much through evaporation and uncontrolled seepage. Instead, drip irrigation delivered water directly to the root zone of each plant. Every drop had a purpose. Young plants received enough water to establish strong root systems. As they matured and became more resistant to drought, the amount of irrigation could be adjusted. Areas that dried more quickly received additional water, while sections that retained enough moisture required less pumping. The system had to operate across very long distances. A broken pipe or a failed pumping station could weaken an entire section of vegetation during the hottest part of summer. For that reason, building the irrigation network was only the beginning. Monitoring and maintenance became permanent parts of the project. Interestingly, the same force that makes Taklamakan so harsh also helps power the system: sunlight. Solar panels were installed near pumping stations and along some planting corridors. During the day, they produced electricity for pumps, moisture sensors, and monitoring equipment. The sensors helped identify areas where soil was becoming too dry. Data allowed operators to decide when pumping should begin and how much water was needed. A weak section of vegetation could be detected early. A leaking pipe could be repaired before hundreds of trees began to suffer. Solar energy also allowed pumping stations to operate far from conventional power grids. This made it possible to maintain vegetation in isolated sections of the desert. But technology did not replace people. Behind every solar panel, sensor, and pump were workers inspecting equipment, repairing pipes, clearing wells, replacing dead plants, and maintaining the system through extreme heat, freezing winters, and repeated sandstorms. Only after grasses and shrubs had created a stable foundation could larger woody plants be introduced. These included saxaul, red willow, and desert poplar, all selected for their ability to tolerate drought, salinity, and extreme temperature variation. A single row of trees, however, could not stop the desert. The protective system had to be built in layers. On the outside were straw grids and sand barriers. Behind them were low grasses. Next came shrubs. Farther inside were taller woody plants. When wind moved out of the desert, it was forced to pass through each layer. Its speed gradually decreased, and its ability to carry sand declined. Some of the sand was trapped in the outer grid. More was stopped by shrubs, while the taller trees reduced the strength of the remaining wind. As a result, far less sand reached roads, settlements, and agricultural land. Separate sections of vegetation were gradually connected. Kilometer after kilometer, the protective system expanded. In November 2024, a green belt measuring approximately 3,046 kilometers was completed around the Taklamakan Desert. This did not mean that the entire desert had become green. The dunes remained, and sand continued to move in many areas. But around vital infrastructure and inhabited zones, people had created a strong enough boundary to reduce much of the encroachment. As the shelterbelts began to work, transportation through the desert became more stable. The best-known route is the Desert Highway, which extends for approximately 522 kilometers and connects areas on opposite sides of Taklamakan. To protect the road, a green shelterbelt approximately 436 kilometers long was established along much of its route. The structure is striking. In the center is the highway. Beside it are pipelines, pumping stations, and rows of protective vegetation. Beyond them lies the open desert. When sand no longer covered the road as frequently, maintenance costs decreased. Vehicles could travel more regularly, and transport times became more predictable. Additional roads were constructed to connect places once separated by Taklamakan. One route reduced travel time between two cities from approximately 6 hours to only 3. The physical distance had not changed, but the time required to cross it had been cut in half. Agricultural products could reach processing facilities more quickly. Machinery, building materials, and consumer goods could travel deeper into remote areas. Service stations, transport centers, rest areas, and local markets began to appear along the highways. Tourism also became more practical. Visitors could travel into the desert to experience the dunes, desert poplar forests, and the unusual sight of a green corridor running through an immense sea of sand. If you are surprised that a highway can survive here, only because millions of plants are being watered and maintained every day, press the like button. It helps more people discover that this is not merely a road-building project, but an entire environmental system working to keep the road alive. The greatest value of the roads and shelterbelts became even clearer in the protected land behind them. Once the sand was more stable, large agricultural estates and specialized planting zones began to develop. Among the most important crops were Xinjiang red dates, also known as jujubes. The trees were planted in orderly rows to make irrigation, pruning, monitoring, and harvesting more efficient. Drip irrigation continued to deliver water directly to the root zone. Soil moisture had to be monitored carefully to prevent both drought stress and unnecessary water use. Farmers pruned branches so that sunlight could reach deeper into the canopy. Weak, damaged, and diseased branches were removed. In some cases, the number of fruits had to be controlled so that the trees would not become exhausted, and the remaining fruit could develop more evenly. Xinjiang's dry climate abundant sunlight, and strong temperature difference between day and night help red dates accumulate sugar and develop their distinctive sweetness. But favorable climate alone does not produce a successful orchard. Every season, growers must inspect irrigation systems, manage nutrients, monitor pests and diseases, protect young trees from strong winds, and follow the development of the fruit. Look at the orchards now extending across the screen. In front are rows of fruit trees. Behind them stands the Shelterbelt. Beyond that, the dunes are still moving. Without the straw grids, shrubs, groundwater, pumps, and protective forest outside, these orchards would be far more vulnerable. The red date trees require years of care before they can produce reliable harvests. During the growing season, water must be delivered at the right time. Too little can weaken the trees and reduce fruit size. Too much can waste a scarce resource and affect root health. As the fruit develops, workers monitor color, firmness, sugar content, and signs of disease. The orchard is not an isolated farm. It depends on roads, pumping stations, power systems, warehouses, and the Shelterbelt that protects the entire production zone. After months of care, the harvest season finally arrives. The green rows begin to fill with deep red fruit. Branches bend beneath the weight. Workers move carefully through the orchard, selecting dates that have reached the correct stage of maturity. The fruit is collected and transported quickly to sorting areas. There, it is separated according to size, color, dryness, and surface quality. The best-looking dates may be packaged for direct sale. Some are dried to extend their shelf life, while others are sent to processing facilities. The harvest is not simply the moment when fruit is removed from the tree. It is the point when the entire transport, storage, labor, and processing system must operate together. Without reliable roads, the fruit may reach factories too slowly. Without storage, part of the harvest may lose quality. Without processing plants, the value of the crop remains limited to a short, seasonal window. Inside the factories, the red dates are cleaned, sorted, inspected, and prepared for different markets. Some are packaged whole, others are dried. Additional portions are processed into red date tea, beverages, food ingredients, extracts, and nutritional products. Through deeper processing, one red date no longer has only one way to be sold. It can become many products, reach different groups of consumers, remain usable for longer periods, and travel to more distant markets. Factories create employment. Warehouses expand. Transport services grow. Trucks carrying finished products leave the processing zones and travel along the same highways that were once repeatedly buried by sand. This is when the true value of the Shelterbelt becomes clear. The forest does not directly produce red dates, but without it, the road, water system, factories, and orchards behind it would be far more difficult to maintain. From here, a connected economic chain begins to emerge. Solar energy powers, pumps, and monitoring equipment. Groundwater supports shrubs and shelter forests. The vegetation holds back the sand and protects highways and farmland. The highways bring machinery and supplies into the region, then carry agricultural products out. Orchards provide raw materials for factories, and the factories turn seasonal crops into products that can reach national and international markets. Tourism, logistics, trade, food processing, and agricultural services continue to grow around this system. A project that began as an effort to stop moving sand gradually became the foundation of a broader regional economy. And build a system strong enough to support life along the desert's edge? If you could choose one product made from these orchards, would you prefer whole red dates, dried dates, red date tea, or a bottled drink? Share your choice in the comments, because it reveals how one crop can support many different industries. Taklamakan remains an enormous desert. Humanity has not defeated it, and the entire landscape has not been turned into a forest. What people have done is understand how the sand moves, identify the places that must be protected. The transformation began with bundles of straw pressed into the sand. From there came grass, shrubs, groundwater wells, solar-powered pumps, shelter forests, highways, orchards, harvests, and processing plants. Each stage depended on the one before it. A highway alone would have been buried. Trees planted without stabilized sand would have died. Orchards without water and shelterbelts would have remained exposed. Factories without roads could not move their products. The success of Taklamakan lies not in one machine, one tree, or one engineering project, but in the way every part was connected into a complete system. Perhaps the greatest lesson from Taklamakan is not that humanity can conquer nature. It is that when people understand natural forces, respect their limits, and work with patience over many decades, even a small bundle of straw can become the first step toward a green road running through a sea of sand.